Hey guys, welcome back to day 23. We are doing resonance and formal charge. We're doing some exceptions to the octet rule today, right, in this video. And so what are some of the exceptions? Obviously, the first exception we've already talked about is hydrogen. And it only gets 2 electrons needed because it wants to be like helium, right? Hydrogen wants to be like helium, 1 has 2, that's it. Now, also, with that, before C, so that'd be boron, beryllium, lithium, and obviously helium and hydrogen. They do not need 8 because they're not to carbon yet. All right, the octet rule really starts with carbon. Now, too many electrons. What do you mean too many? Right. So elements in the below period 2. So that means period 3 and below. Right, which would include It would include Si, although we never do Si. P, S, Cl. It would include argon, but we're not going to do any argon compounds on Earth. Right? It would include arsenic. Right? It would include selenium, bromine, krypton. It would include tellurium. It would include, I guess it would even include antimony if we made compounds with antimony. Right? Iodine and xenon, right? So that's period, right? This is period 3, 4, 5. Okay. So though they can have more than 8. How do we know? Well, they make compounds that exist with more that would need more than 8 valence electrons, right? So we'll show you some examples, but they exist. And finally, odd number electrons, radicals, free radicals. You might have heard of those. They have an unpaired electron. Right now, they're less than 10% of reactions. However, you talk about like some biological reactions, they're important, and they do exist, and they are very reactive. Right? They're very reactive. The first thing we're going to talk about is formal charge today. All right? The formal charge is the charge it would have if all the bonding electrons were shared equally between the bottom atoms. Now, in the last video, we talked about that these atoms don't share, right? Like if you guys go into Subway or any other Jersey Mike's or any other sandwich shop and you're going to split a sub, right? You expect the sub to be cut down the middle. Well, that's how we're doing formal charge. We're taking the bond and cutting it down in the middle. We each get 1 electron. Okay, that's not how really they share. They don't share that way, but that's how we're going to do it. Now, the formal charge adds up to the charge on the ion. All right, and so if there's no charge, it adds up to 0. If it's -1, the formal charge should add up to -1. Right. Also, when we do this, the more electronegative atoms tend to be negative. That's ideal, right? That doesn't always happen, though. And then we minimize formal charge if possible. We want to make the formal charges as low, close to 0 as possible. Doesn't always work. All right. Okay. So let's do an example. Not here first. Let's just do O2. Oxygen, gas. O to O, right? We have 2, 4, 6, 8, 10, 12 electrons. There's O2. The formal charge of O2 is 0. Okay? And so basically these electrons these are 2 electron bonds, up, down, and then up, down, right? What happens is you break the bond in half, right? And so the oxygen on the left gets 2 of the orange arrows and then all the purple dots. So it has 6 electrons. And it brings in 6 valence electrons, so it's formally 0. The oxygen on the right gets 2 of the orange electrons, as well as all the pink electrons, which is 6. Okay? All right, it gets 6 electrons right here. It goes 1, 2, 3, 4, 5, 6. So it has 6 electrons. It brings in 6 electrons, and so formally it's 0. Right? It's like going to a casino. If you walk in with $20 and leave with $20, you broke even. right? I don't recommend casinos because most people don't break even. Okay, so that's how we talk about formal charge. And for here, we know it's, delta En is 0. There's no uneven distribution there. N2O is different. And so we count the electrons, 2 electrons, right? Or not 2 electrons. How about 2 times 5 electrons plus 6 electrons gives us 16 electrons. Now, central atom, typically written first and least electronegative. Well, who's written first? Nitrogen, and nitrogen's less electronegative than oxygen. So we're going to go with it. N, O, right? I've had many students put O in the middle. Well, what happens if you put O in the middle? We'll do that, all right? I'm going to do it right here on the side before we do SCN. So we got N, O, N coming up. First thing we do is bond them. 2, 4. Then we fill in the octets. 6, 8, 10, 12, 14, 16. Is that good? Well, the nitrogen on the left. 1, 2, 3, 4, 5, 6, 7, 8. Good. The oxygen on the right. 2, 4, 6, 8. Good. Nitrogen in the middle. 4. Not good. Well, what are my options? Well, I can double bond each side. So we're going to do that first. And we'll go with a double bond each side. But now, could I have done it differently? In fact, there's 2 other ways I could do this. Do it the green way, where I triple bond one side and single bond the other, right? And so if I were to do that for you, we're here. Oh, that was weird. All right, we have the same setup as before, right? With the pink dots. Now we got the green dots. I can triple bond, so that would mean I would take those and those and make a triple bond. But I could do it the other way too, in blue here. I could triple bond the oxygen. So those are all 3, so these are 3 valid Lewis structures. 3 valid Lewis structures. All right. And if you noticed, I'm moving the electrons and not the atoms. Okay? All right. Well, which one's best? Let's talk about formal charge. And I'm going to put in red here, up, down, up, down, up, down, up, down, right? That's what's going on here, right? So each of those bonds has 2 electrons. And we are going to break them in half. Right there, right there. We're going to do it for all of these too, right? We're going to do it for all of these. All right, formally. Again, nitrogen brings in 5 valence electrons. Oxygen brings in 6. So formally, this has 1, 2, 3, 4, 5, 6. It has 6 valence electrons. So nitrogen has 6, but it brought in 5. It has an extra electron. So formally, oxygen here is -1. I'm sorry, that's nitrogen. Nitrogen is -1. The nitrogen in the middle has 1, 2, 3, 4. Has 4 electrons. It brought in 5 electrons. It lost an electron, so therefore it is formally +1. And then the oxygen. 1, 2, half of each bond. 3, 4, 5, 6. So it has all those. Well, if it has 6 and it brought in 6, we're good. It's formally 0. That's pretty good for formal charge. Now let's look at the green. We have nitrogen on the left. 1, 2, 3, 4, 5. It has 5. It brought in 5. So formally it is 0. The nitrogen in the center has 1, 2, 3, 4. Has 4 again. Brought in 5. So it lost 1. So formally it's plus 1. Right? Now again, there's no actual charge. This is the formal charge. When we talk about how they're bonding and how they're situated and if they're stable or not stable, if they're happy, not happy, so to speak. Oxygen has 1, 2, 3, 4, 5, 6, 7. Has 7. Brought in 6. That means it gained 1. So it's formally minus 1. The blue one. Let's look at the blue one. So nitrogen on the left. 1, 2, 3, 4, 5, 6, 7. Nitrogen on the left has 7. Brought in 5. So if it has 7 and brought in 5, it gained 2 electrons. So formally it's minus 2. The middle one. It's the same, isn't it? It's going to be plus 1. Let's do it. It has 1, 2, 3, 4 again. It brought in 5, so it's plus 1. Oxygen has 1, 2, 3, 4, 5. It has 5 electrons, but it brought in 6, so it's down 1, so that means it's plus 1. All right. We want to minimize formal charge if possible. Which one does that take off? This one's probably the worst. Right? Why? Because I have all 3 atoms have a formal charge. Whereas here I have a 0 and here I have a 0. So the next question is, which one is better? Oxygen being 0 or nitrogen being 0? Well, the more electronegative atoms tend to be negative. So who's more electronegative, N or O? Turns out it's O. So this becomes the best structure. What if we'd have done it over here this way? 2, 4, 6, 8, 10, 12, 14, 16. You hit the double bond. It probably wouldn't have mattered what you did. But formally, we'd had 1, 2, 3, 4, 5, 6. Formally, this is minus 1 and minus 1. And oxygen 1, 2, 3, 4 has 4 brought in 6. It's plus 2. That's really bad. That's the most electronegative element being plus 2. That's why the least electronegative element is typically the central atom. All right. My challenge to you right now is to pause the video and try the next one. All right. Try this next one. You have 6 electrons plus 4 electrons plus 5 electrons plus 1 electron is 16 electrons. And it is SCN. And you have 3 of them. There are 3 SCN options. And you probably will realize they're very similar to this. So go ahead and pause, do it, see what you get, and then come back. All right, hope you paused and tried it out. So first thing we got to do is bond them. So 2, 4, 6, 8, 10, 12, 14, 16. And if you notice, it's 16 electrons, 3 atoms, just like the one before. So the 3 options are going to be the same as the one before. I could double bond both sides. I could triple bond the sulfur. Or we could triple bond the nitrogen. And now we got to figure out the formal charges of everything. Well, let's look. 1, 2, 3, 4, 5, 6 for sulfur. Sulfur has 6. How many does sulfur bring in? It brings in 6. So formally, that's 0. Carbon. In carbon, if you look, carbon's the same. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Carbon's the same in all of them, right? And carbon has 4 and brought in 4. Carbon is actually 0 in all of them, which is nice. So that's consistent. All right, back to the blue one. Nitrogen. 1, 2, 3, 4, 5, 6. Nitrogen has 6, brought in 5, so it's formally minus 1. All right. In the middle, pink. 1, 2, 3, 4, 5. Sulfur has 5, but it brought in 6, so it's formally plus 1. Nitrogen. 1, 2, 3, 4, 5, 6, 7. 7 has 7. Brought in 5. Formally minus 2. Purple. 1, 2, 3, 4, 5, 6, 7 for sulfur. Brought in 6, so that's formally minus 1. And nitrogen here. 1, 2, 3, 4, 5. Has 5, brought in 5, formally 0. Well, which one is the worst? Pink one in the middle, right? I got 2 atoms with formal charges, all right, and they're not minimized. I have a minus 2, whereas the purple and the blue have only 1 minus 1 charge. So the purple and the blue are automatically better than the pink. Now, who's more electronegative, sulfur or nitrogen? Well, if you look at the top 5, FOClN ends in the top 5. So that means those are the best. All right. This leads us to resonance. All right, let's define resonance. Okay. A molecule with 2 or more valid Lewis structures. Well, the one on the screen has 2 or more valid Lewis structures. In fact, it has 3 valid Lewis structures. Right? And so in Chem 151, or usually in all Chem 1, right, we don't mention that what we just did right here, all of those are technically resonance structures, but they're not equivalent because the formal charge changes, right? See how the electrons, I have 2 double bonds on each side, then I have a triple bond and a single bond, right? And if you look, you got two lone pairs versus 1 lone pair versus 3 lone pairs, right? The electrons are moving around. We can move the electrons around, but we're not moving where S, C, and N are. They're all in the fixed position. All right? Okay? And so a molecule with more than 1 valid Lewis structure is resonance. Okay? Some of you have this. I have a wedding ring and a watch. If I take my wedding ring off and put it on the other hand, it's a new arrangement of wearing the ring. If I take my watch off and put it on the other wrist, it's a new arrangement of wearing the watch. However, if I'm looking at myself in the mirror and I do 180 degrees, so I'm now facing away from the mirror, the watch and the ring are on the opposite side before my turn. If I turn and rotate, that's not moving the electrons. All right, if that makes sense. Okay, it's only the electrons have to move without the atoms moving. Okay, so we will, for examples like O3, the formal charge does not change among the oxygens. The formal charge can move, but overall doesn't change. Where here, each atom, like if you look at nitrogen goes from -1 to -2 to 0. Right, so those are unequivalent resonance structures when it comes to formal charge. But they're still technically resonance structures. If you take organic chemistry, those are resonance structures. Just in Chem 1, we don't really dive into that. We do this, O3. All right? So, by the way, for formal charge, this tells us which is the best structure, best resonance structure. Where here, these, they just have resonance. So O3, if we do O3, we have 3 times 6 electrons. So a total 18 electrons. O, O, O. So 2, 4, 6, 8, 10, 12, 14, 16. Extra electrons go on the central, 18. All right, now we have options. I can double bond. I can take 2 away and make a double bond there. Or I can take 2 away and make a double bond there. Right? So there's 2 ways to draw this. And so in blue, we'll do the left, oxygen. Then I'll show you the pink. All right. So those are 2 valid Lewis structures where the double bond goes from side to side. So resonance is resonating, right? A violin string, example, where you pluck it, or a guitar string, and it goes back and forth. It resonates, right? So this double bond moves back and forth. That's resonating. Okay, so the actual structure is a mixture of the two, but we can't really draw it with the octet rule. All right. Okay, and so the actual bonds are, they're basically the oxygen-oxygen bonds are like 1.5 bond strength. They're not double bond strength, they're not single bond strength, they're in the middle. All right. A couple more examples. Carbonate. Electrons. 4 plus 3 times 6 plus 2 for the charge. So that would be what? 24 electrons. All right. C, O, O, and O. All right. 2 minus. Bond them. 2, 4, 6, 8, 10, 12. 14, 16, 18, 20, 22, 24. Well, what's the problem there? Carbon doesn't have 8. So it doesn't matter what oxygen, took the black one, double bond. But could I double bond from the blue? Yes. Or the green? Yes. And so there's more resonance structures because of this. Right? And we do this. Right, so if I draw them all out, the double bond could be the blue. Or the double bond could be at the green, oxygen. All right, so now if you look, that double bond is basically going around from black to blue to green, or if it goes from green to blue to black. It doesn't matter the order, the direction, okay? We're just saying it goes around, right? And it resonates between all 3 oxygens and carbon, right? So that's resonance. And if you notice, the double bond's moving, not the atoms. Last but not least, acetate here. We have 2 times 4 electrons plus 3 times 1 electron plus 2 times 6 electrons plus 1 electron. So that would be 24 electrons again. All right. Now how this is arranged, right, you have HC. So you'll have a CH3, a C, an O, and an O. And we bond 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Well, carbon's not good. And so most of the times you'll see this written where this oxygen is double bonded. However, we could have double bonded a different oxygen, couldn't we? We could have double bonded that oxygen. And so those are the two resonance structures of acetate, where that double bond goes back and forth. Right. Hopefully that makes sense with resonance. Radicals are next. Okay, and then we've got expanded octets. So radicals, odd numbers. NO, 5 electrons plus 6 electrons is 11 electrons. Oh, she's black. And to O, 2, 4, 6, 8, 10, 11. There's your radical. Now that doesn't work for electrons. If I double bond, 2, 4, 6, 8, right? Now, is that better, or is this one better? Which one's better? All right, what do you think? Well, how do we tell? Formal charge. 1, 2, 3, 4, 5, 6. Oxygen has 6, brought in 6. 2, 3, 4, 5. Nitrogen has 5, brought in 5. You can't beat that. That's formal charge of both 0. Here it's 1, 2, 3, 4, 5, 6. Nitrogen's minus 1. And 1, 2, 3, 4, 5. Oxygen's plus 1. So that is the worst one. That one is a valid Lewis structure, but not nearly as good as this one. Now, can I triple bond? Could I take these 2 electrons away and make a triple bond? No, because it'd be 2, 4, 6, 8, 9 for nitrogen, and nitrogen cannot exceed 8. All right. Superoxide, same thing. You got 2 times 6 electrons plus 1 electron gives us 13 electrons. So we have O and O. 2, 4, 6, 8, 10, 12, 13. So superoxide has an unpaired electron. And it doesn't matter what oxygen you have because the same thing, same formal charge. So those are 2 radicals for you. And now we have expanded octets. 12 electrons up to. Wow, how does that work? Well, let's look. Sulfur has 6 electrons plus 6 times 7 electrons. So that's 48 electrons. That's a lot of electrons. Well, who's the central atom? Well, hopefully by now we know it's not fluorine, right? And so who's written first? It would be sulfur, least electronegated. So I have S with 1, 2, 3, 4, 5, 6. 2, 4, 6, 8, 10, 12. And you fill in the octets, 14, 16, 18. Maybe you guys know 6 times 8 is 48. So we're going to go right through. Oh, I erased part of my F there. And get all the electrons in. And if you count them, you'll get all 48 electrons. And that is the Lewis structure of SF6. And that compound exists. We use it as a different, not the one you probably have at home, but it is a fire extinguisher. It's in a fire extinguisher that's used. All right, sulfur hexafluoride. And so, yeah, it exists. Violates the octet rule, but there it is. All right, and since sulfur's in the 3rd period and below, it can do it. Xenon tetrafluoride, another one. I have 8 electrons plus 4 times 7 electrons. So that's 36 electrons. Right, 4 All right, we bond 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Well, there's some more electrons. 34, 36. Extra electrons goes on the central atom as lone pairs. And there you go. There's a xenon tetrafluoride. It works. It has 2, 4, 6, 8, 10, 12 electrons around a xenon. But if you look at these, what's their formal charges? Sulfur, right here, the sulfur has 1, 2, 3, 4, 5, 6. Has 6, brought in 6, it's happy. Xenon has 1, 2, 3, 4, 5, 6, 7, 8. Brought in 8, it's happy. It's 0. And so formal charge actually works for these, which is kind of neat. Alright, I think we have some more. Sulfuric acid, triiodine, and bromine trifluoride. Alright, 3 more to do. Now, my recommendation, again, pause me, do them, see if you can get them. Alright, hopefully you paused and you tried them. First thing is electrons, 2 times 1 electron, plus 6 electrons, plus 4 times 6 electrons. So 32 electrons. Now these ternary oxyacids, right? You have sulfur with 4 oxygens, and then you have the hydrogens on the oxygens. It doesn't matter which ones. I just picked opposite. It does not matter. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Now, that works out. And in fact, that's not a violation of the octet rule, is it? Because sulfur has 8. Let's check something, though. What is the formal charge of hydrogen? Well, H here, 1 electron, is happy. Oxygen here, this oxygen, 1, 2, 3, 4, 5, 6. Perfect. Same with this one, 1, 2, 3, 4, 5, 6. The oxygens on top and bottom, right, they're the same. So down here, I got 1, 2, 3, 4, 5, 6, 7. Right, just like I have up top, 1, 2, 3, 4, 5, 6, 7. They're both minus 1. Sulfur here, 1, 2, 3, 4, has 4, but it brought in 6. Here's how we can minimize formal charge. Oh, if I do that and that, what happens to the formal charge? Sulfur now has 1, 2, 3, 4, 5, 6. Brought in 6 happy. Each oxygen is 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. So now the formal charges are 0. But now sulfur is violating the octet rule. All right. Now, when you're doing homework, all right, or doing tests, make sure you note whether it tells you to minimize the formal charge or complete the octet. If you complete the octet, all you need to do, right, completing the octet is that. That's completing the octet, right? There's no double bonds. Everything's happy with 8. You're good. If you want to minimize formal charge, that's the way you got to do it. Okay? So just be mindful of what it actually is saying. So make sure when you read the problem, you notice that. I3 minus. Let's see what you got. 7 electrons. There's 3 of them plus 1, which should be 22 electrons. I. Let's try it in a line. Let's see here. 2, 4, 6, 8, 10, 12, 14, 16, 18, 2022. And that's the best Lewis structure, right? The terminal eyes, right? The terminal eyes, that's this eye and this eye are the terminal eyes, right? 1, 2, 3, 4, 5, 6, 7. Have 7, brought in 7, 0. In the middle eye, the central eye, 1, 2, 3, 4, 5, 6, 7, 8. Has 8, but it brought in 7, it's -1. We need to be -1. That's the best we can do. All right, last one. Bromine trifluoride. Let's see. It's 7 electrons plus 3 times 7 electrons. So that's 28 electrons. Who's in the middle? Not fluorine. So Br, F, F, F. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 24, 26, 28. And if you check the formal charge of those, I think we're good. All right, everybody's has 7, brought in 7, but bromine has 2, 4, 6, 8, 10 electrons. So it violates the octet rule, but because it's in the third period and below, it works. All right, yep, the next up is shapes. So how about that? So right now, that is resonance, formal charge, and exceptions to the octet rule with extra electrons. I hope that makes sense. If you have any questions, let me know. Otherwise, we'll take care, guys. See ya.